this episode, we're going to zoom in on what happens after compute is deployed and running, because that is the moment when attackers try to turn access into action. Even with hardened images, reduced services, and strong patch cadence, there is still a chance that a workload gets compromised through a stolen credential, a misconfiguration, or a newly discovered weakness. Runtime protections exist for that exact reality, acting like safety rails inside the workload while it is active and processing real traffic. The big idea is not that runtime protections replace prevention, but that they limit what an attacker can do after they get in, especially around execution, persistence, and privilege. Beginners sometimes assume that once an attacker runs something, the game is over, but modern defenses aim to contain damage and slow attackers down. By the end, you should understand what runtime protections are at a high level, why they matter specifically in cloud workloads, and how limiting execution, persistence, and privilege creates a smaller and more defensible environment. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Runtime is the period when a workload is actively running, meaning processes are executing, data is being handled, and services are communicating. This is different from build time controls, which shape what gets deployed, and different from configuration checks, which validate what is supposed to be true. At runtime, the system is alive, and that is when an attacker's actions become meaningful because they can try to run commands, install tools, and alter the environment to stay longer. In cloud systems, runtime is also when workloads interact heavily with other services, often using tokens or roles to access storage, secrets, and APIs. That makes runtime protections especially important because a compromised workload can become a pivot point into other parts of the environment. A beginner-friendly way to think about runtime protection is that it is the difference between locking the doors before you leave and having an alarm system that detects and restricts movement if someone breaks in anyway. Both are valuable, and runtime controls focus on the moment of intrusion. Limiting execution is about controlling what code and processes are allowed to run inside a workload. Attackers often rely on executing new tools, scripts, or payloads after they gain a foothold, because those tools help them explore and expand. If the environment allows arbitrary execution, an attacker can bring in whatever capabilities they need, which increases risk quickly. Runtime protections that limit execution aim to restrict this ability, making it harder to run unapproved binaries, start unexpected processes, or use interpreters in ways that violate policy. The goal is not to block the workload's legitimate functions, but to constrain the system so it does not become a general-purpose playground for an attacker. Beginners sometimes worry that limiting execution will break applications, but in many workloads the set of required processes is actually narrow and predictable. When you design around that predictability, execution controls become a powerful containment mechanism. Execution limits also matter because cloud attackers increasingly try to blend into normal behavior by using built-in features rather than obviously malicious tools. For example, they may use standard system utilities, scripting environments, or common libraries already present on the system. That means limiting execution is not only about blocking unknown files. It is also about controlling how legitimate components can be used. If a workload should never run a shell, then a shell process starting is a strong signal and can be restricted. If a workload should never write new executable files to disk, then attempts to do so can be blocked or flagged. These constraints reduce attacker flexibility and make abnormal actions easier to detect. When execution is constrained, the attacker must work harder and may trigger more visible signals in the process, which improves your chances of catching the compromise early. Limiting persistence is the next major goal because attackers prefer to stay in environments long enough to find valuable data and establish reliable access. Persistence is achieved by creating something that survives beyond a single process or session, such as scheduled tasks, modified startup settings, newly created accounts, or planted backdoors. In cloud compute, persistence can also involve modifying application code, changing configuration files, or altering automation scripts that will redeploy attacker access later. Runtime protections that limit persistence aim to reduce the ability to write to critical locations, change startup behavior, or modify system components. A simple way to picture this is that an attacker wants to leave a hidden key under the mat, and persistence controls aim to remove the mat and lock down where keys can be stored. When persistence is harder, compromise becomes more temporary and easier to eradicate with replacement or redeployment. The cloud environment adds an important twist to persistence because compute instances are often meant to be replaceable, especially in immutable patterns. If a workload is designed to be short-lived and stateless, then local persistence mechanisms become less valuable to attackers because the instance may be replaced regularly. Runtime protections reinforce this by making local changes harder and by ensuring that the running system stays close to its intended state. If an attacker cannot modify startup settings or plant files in expected persistence paths, they may be limited to the lifetime of their current access. That can turn a potentially long-term breach into a shorter event that can be contained more easily. For beginners, the key insight is that persistence is not a single trick, it is a strategy, and runtime protections are meant to disrupt that strategy. When you disrupt persistence, you reduce the attacker's ability to operate patiently. Limiting privilege is the third pillar, and it is often the most important because privilege determines how much damage can be done. Privilege inside a workload includes operating system privileges, access to sensitive files, access to credentials or tokens, and the ability to interact with cloud APIs through assigned roles. Attackers commonly seek higher privilege because it enables them to disable defenses, access secrets, or pivot to other resources. Runtime protections that limit privilege work by enforcing least privilege in practical ways, such as ensuring processes run with minimal permissions and restricting access to high-value resources. Even if an attacker gains execution in one process, they should not automatically gain administrator-level control. This separation reduces blast radius and slows attacker progression. It also creates more points where detection can occur because privilege escalation attempts tend to produce anomalies. Privilege limitation also connects to how workloads access cloud services, because many cloud workloads rely on roles and tokens rather than static credentials. If a workload is assigned overly broad permissions, an attacker who compromises that workload can use those permissions to access data or modify infrastructure. Runtime protections can help by limiting how credentials and tokens are accessed within the workload and by restricting which processes can use them. For example, if only the application process should use a specific token, then other processes accessing it may indicate compromise. This concept is easier to grasp when you think of tokens as keys that should stay in the hands of a single trusted process. If every process can reach the keys, then compromise of any one process becomes much more dangerous. Limiting privilege inside workloads is therefore not only about operating system permissions, but also about how cloud access is scoped and protected at runtime. Another beginner misunderstanding is assuming that runtime protections must be perfect to be useful. In reality, even partial restrictions can change the attacker's cost and timing. If an attacker cannot easily write to disk, they may have to operate purely in memory, which can be harder and riskier. If an attacker cannot run common utilities, they may need to use more complex techniques that are more likely to be detected. If privilege escalation is blocked or slowed, the attacker may fail to reach their objective before defenders notice. Runtime protections are about shifting the balance, not about guaranteeing that no compromise can ever occur. This mindset helps you appreciate why layered defenses matter, because each layer adds friction and reduces attacker options. When an attacker's options shrink, your environment becomes more resilient. Runtime protections also generate valuable signals for monitoring and investigation. If a control blocks an attempt to execute an unexpected process, that is a clue that something inside the workload is trying to behave outside its normal function. If a control prevents a write to a sensitive system location, that is a clue about attempted persistence. If a control detects privilege escalation behavior, that is a clue about attacker progression. These signals can be correlated with network flows, identity events, and posture findings to build a stronger narrative. For example, a suspicious login followed by blocked execution attempts inside a workload paints a clearer picture of compromise than a login anomaly alone. This is why runtime protections support detection as well as prevention, because they turn attacker actions into visible events. Visibility is a defensive advantage, especially against stealthy cloud attackers. Design choices at deployment time can make runtime protections more effective, which is another reason these topics connect across episodes. If you build minimal images and reduce services, there are fewer legitimate processes and fewer legitimate write paths, which makes restrictive runtime controls less likely to break normal operations. If you follow immutable patterns, local changes are less necessary, so blocking them is more reasonable. If you enforce baselines, you have a clear understanding of what should be running, which helps define what should be allowed at runtime. In other words, runtime protections are easier to apply when the workload is predictable. Beginners sometimes treat runtime controls as something you bolt on later, but they work best when the workload is designed to support them. Predictability makes restriction safe, and safe restriction makes compromise harder. It is also worth emphasizing how runtime protections help with the specific cloud problem of shared responsibility. Even though cloud providers secure the underlying infrastructure, you are responsible for what runs in your workloads and how it behaves. Attackers target the parts you control, such as application logic, operating system configuration, and access permissions. Runtime protections are one of the ways you actively manage your side of responsibility while the workload is operating. They can reduce the chance that a compromise turns into a large incident that impacts other cloud resources. They also provide a way to enforce security expectations continuously, not just at build time. This is a practical way to close the gap between the speed of cloud operations and the need for control. When you combine execution limits, persistence limits, and privilege limits, you get a workload that is harder to exploit deeply, even if it is breached. The attacker might still be able to perform some actions, but those actions are constrained and more likely to trigger detection signals. That containment changes the outcome of many incidents because it reduces blast radius and buys time for response. In cloud environments where attacks can move quickly, buying time is valuable because it allows defenders to isolate systems, rotate credentials, and replace compromised compute before the attacker reaches sensitive data. This is why runtime protections are not just technical preferences, they are strategic defenses. They shape how incidents unfold, often turning catastrophic outcomes into manageable ones. To close, applying runtime protections is about making the inside of your workloads a controlled space rather than an open workshop for anyone who gains entry. Limiting execution reduces the attacker's ability to run new tools and scripts. Limiting persistence prevents them from planting long-lived footholds, and limiting privilege keeps compromised processes from gaining broad control. These protections matter in cloud compute because workloads are interconnected, and a single compromised workload can become a bridge to other services if it has too much freedom. Runtime controls also improve monitoring by producing signals when attacker-like behavior is attempted, and they align naturally with hardened images, reduced services, immutable patterns, and baseline validation. For a beginner, the most important lesson is that security is not only about blocking entry, it is also about controlling what happens after entry is attempted or achieved. When you constrain execution, persistence, and privilege at runtime, you create a safer environment where compromise is harder to deepen and easier to detect.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.